Welcome to this explainer. Today, we are undertaking a precise, highly technical analysis of a fundamental architectural challenge in advanced AI research, defining the exact conditions required for recursive self-improvement. Most theoretical accounts of recursive self-improvement actually begin much too late. They tend to assume an intelligence engine already exists, focusing strictly on how its internal updates should be evaluated, aligned, or governed. The paper we are analyzing today argues for a radically different and rigorously defined thesis. Recursive intelligence is produced when a system repeatedly changes the very structural conditions through which its future reasoning is generated. We will examine how this phenomenon emerges not from mere inference iteration, where a fixed architecture simply performs more reasoning or more search, but from durable, verifiable structural changes to the underlying machinery of thought itself. Our analysis will follow this specific architectural progression. We'll begin by distinguishing repeated inference from recursion. Next, we'll detail the structural mechanisms of intelligence production, followed by the integrated recursive cycle. Then, we'll examine controlled inheritance, outline a falsifiable experimental design, and conclude with a strict criterion for recursive self-improvement.
Section 1. Repeated inference versus recursion.
To begin, the paper argues that we must strictly distinguish a system that simply performs more search from a system that genuinely changes its productive structures. Let's consider repeated inference. You might have a conventional workflow that adds latent reasoning steps, verification loops, or external tool use to a base model. Yet, repeated execution of a fixed architecture is still only repeated inference. It means a fixed architecture performs more reasoning or search, but it leaves behind no durable productive change in the system's underlying state. Conversely, recursive intelligence production means that each cycle actively changes the structures that generate future reasoning. When an architecture changes structurally, successful reasoning trajectories are abstracted into reusable cognitive operators. Consequently, future search over a similar mathematical or logical domain becomes structurally more efficient. This brings us to a foundational concept. Recursion begins precisely when reasoning changes the machinery that produces future reasoning. This distinction is absolutely critical, because it fundamentally shifts our unit of analysis. We are no longer evaluating the immediate, isolated output produced at time t, we are evaluating the evolving, productive intelligence state of the system itself. This state dictates what specific variables can be represented, which search topologies can be navigated, and what logic can be compressed in the very next computational cycle. Section 2. Mechanisms of intelligence production. To physically achieve this transformation of the productive state, the proposed architecture relies on 5 independent yet tightly coupled structural mechanisms. We will systematically dissect these 5 requirements: representation restructuring, energetic allocation, search topology, recursive operator formation, and structural memory.
The first proposed mechanism is representation restructuring. A structurally superior representation fundamentally changes which causal variables, hidden constraints, and conceptual distinctions are analytically reachable. This is not simply a matter of pruning a localized search tree, it is actively altering the ontology of the problem space. By transforming latent constraints into explicit, computable variables, the system actively reduces effective search complexity. Crucially, a better representation ensures that entirely new, high-value solution paths transition from being mathematically unreachable to highly accessible.
The second mechanism is energetic allocation. In this framework, energy is treated strictly as a finite capacity. This operational budget encompasses raw compute, generated tokens, experimental testing, memory retrieval, automated verification loops, and, critically, human review. Intelligence systematically improves only when these finite resources are dynamically redirected away from low-yield inference and explicitly allocated toward computational transitions that offer the highest marginal structural return. If a system cannot reallocate its finite energetic capacity toward structural improvement, it cannot recursively amplify. Third, we examine search topology. A truly recursive system does not simply traverse a static, predefined state space. It actively modifies the graph of reachable reasoning states. A recursive system can mathematically restructure the search graph by adding highly useful transitions, permanently removing known unproductive paths, and deliberately delaying early commitment to preserve alternative high-value subgraphs. In doing so, it effectively alters the physical topology over which all future latent reasoning will be conducted. The fourth proposed mechanism is recursive operator formation. When a system successfully traverses a complex trajectory, that trajectory must be abstracted into a reusable cognitive operator. However, simple rote caching is strictly insufficient. The paper argues that valid operators must rigorously demonstrate verifiable compression of the reasoning cost. They must demonstrate robust transfer to novel instances, strict faithfulness to the underlying causal structure, and composability without generating architectural interference. Furthermore, the strongest form of this mechanism involves the abstraction of meta-operators. These are specialized operators whose precise function is to recursively improve future operator formation itself. The fifth mechanism is structural memory. While ordinary contextual memory simply stores text or strings, structural memory rigorously preserves the precise architectural parameters of future intelligence. This explicitly includes successful and failed causal decompositions, validated operators, quantified uncertainty bounds, strict proof obligations, cryptographic provenance, and detailed repair histories. However, preserving everything leads to pathological data contamination and path dependence. Therefore, purposeful forgetting is an absolute architectural necessity when retained structures threaten to contaminate the fidelity of future reasoning cycles. Section 3. The integrated recursive cycle. These 5 independent mechanisms must seamlessly integrate into a continuous, multi-generational state transformation loop. The integrated cycle proceeds sequentially. The system must first represent the conceptual space, then allocate its finite energetic budget. It must traverse the modified search topology, abstract the successful latent paths into valid operators, remember the productive structures, qualify the candidates against strict empirical thresholds, and finally, inherit the validated structures. Consequently, the result of a complete cycle is not simply a better answer to an isolated prompt. The result is a better state space, a more efficient search policy, a vastly improved operator set, a cleaner memory structure, and a highly refined allocation rule. Section 4. Controlled inheritance and governance. Having defined the productive mechanisms, the paper precisely delineates the architectural boundary of governance. Governance enters this framework strictly at the point of inheritance. The paper argues that governance does not and cannot create the new cognitive operator. Instead, it serves as a hard-coded critical safeguard. It decides whether a candidate structure is valid enough to become part of the next productive base state. The core philosophical and architectural tenet here is that the improver should never be the sole trusted judge of its own structural improvement. Because the system cannot unilaterally approve its own modifications, qualification dimensions must be strictly formalized. Candidate architectures are qualified across several absolute dimensions: base capability preservation, transferability to entirely unseen tasks, temporal stability, undeniable provenance, and measured resource cost. Crucially, the architecture demands structural reversibility, allowing a corrupted structural update to be rolled back without cascading failure. Finally, governance must verify future improvability. It must ensure that a candidate structure does not optimize for immediate localized benchmark scores at the expense of permanently bottlenecking the system's capacity for future recursive amplification. Section 5. Falsifiable experimental design. This distinction is experimentally testable. Theoretical assertions regarding recursion demand empirical, falsifiable validation. The paper provides a highly constrained experimental design comparing 4 precise conditions. First, a fixed workflow condition, characterized entirely by repeated inference with 0 persistent productive state modification. Second, naive recursion, a system that blindly retains any structural change that boosts an immediate target score. Third, governed recursion without explicit productive restructuring mechanisms. And finally, full recursive production, utilizing the integrated structural mechanisms operating beneath controlled inheritance. This controlled setup isolates the exact measurable efficacy of productive restructuring versus mere search or governance alone. To validate the architecture, decisive empirical evidence of success requires demonstrating sustained, multi-generational improvement across specific metrics. Researchers must mathematically document a sustained increase in improvement production efficiency. We must observe verifiable transfer to unseen tasks and persistent operator reuse across disparate domains. Furthermore, the evidence demands measurable search cost reduction over successive generations, superior allocation quality, guaranteed recoverability, and unwavering lineage stability. Lineage stability is perhaps the most critical metric, as it proves the recursive mechanism has systematically avoided terminal structural corruption across generations. The claim remains bounded by severe predetermined failure modes. The thesis is considered falsified or significantly weakened if the abstracted operator transfer fundamentally fails in practice. It is weakened if the observed gains disappear entirely when tested on hidden task distributions. Importantly, if later generations stagnate and fail to become systematically better improvers, the architecture has failed. Most crucially, if the empirical gains are explained only by the sheer injection of more compute, or if full productive restructuring adds zero statistically significant advantage over governed recursion alone, then the proposed mechanism is effectively invalidated. Further empirical validation is necessary to continually probe these boundaries.
Section 6. The RSI criterion.
This rigorous experimental framework leads us to an operational definition of recursive self-improvement. We establish the strongest RSI criterion. A successor should not merely perform better on an external benchmark. Instead, a true successor must become structurally better at producing validated future improvements. The defining characteristic of a recursively self-improving system is that its primary, measurable output is the increased capacity to discover, evaluate, and implement further structural enhancements over its parent state. Crucially, this framing clarifies why recursive self-improvement can genuinely begin long before a system achieves direct weight self-modification. A fixed-weight base model can continually restructure the productive conditions of its reasoning. It can actively improve its representations, its latent search policies, its internal operators, its memory structures, its experiment selection heuristics, and its allocation rules. The paper argues forcefully that weight updates alone are not recursively productive unless they inherently improve the machinery that produces future updates. To conclude our analysis, we return to the core thesis. Recursive intelligence is produced when each reasoning cycle improves the structures that generate the next cycle of reasoning. We have established that controlled inheritance preserves recursive intelligence, but representation restructuring, resource allocation, operator formation, and structural memory are what produce it. By optimizing the very architectural conditions under which future computation occurs, we move from mere repeated search into true self-amplification. Which leaves us with a critical, verifiable question for the field moving forward. If a model can structurally augment its own cognitive topology and operator abstraction without altering its base weights, how rapidly can we empirically detect the emergence of a system whose absolute highest yield output is simply the generation of its own successor?